Okay, so in this video, I'm just going to introduce the derivatives of vector functions. And first, let's recall from Calculus 1. When we have a function y equals f of x, we know that by definition, our derivative f prime of x is the limit as delta x, sometimes we call that h, but as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Again, delta x, sometimes we write that as h. And this means the slope of the tangent line at a point. So it's very similar when we think about vector functions. So we're going to define the derivative of a vector function, r prime of t, will be, since our independent variable is t, we're going to write the limit as delta t approaches 0 of r of t plus delta t minus r of t over delta t. If we think about what this represents visually, notice in the diagram below, I have a position vector pointing to point P on our curve r of t, and a position vector pointing to point Q on the curve r of t. Let's suppose that we've gotten to Q by adding a little delta t to t and evaluating r of t plus delta t. That's going to give us, if we draw the secant vector from P to Q, we get a vector from P to Q, and as delta t gets smaller, we are imagining a dynamic Q moving closer to P. And you can see that our secant vector is going to approach a tangent vector, which I'm going to draw in a little bit in a very small red vector. And that little vector that's tangent to the vector curve at point P is what we're going to call r prime of t. So r prime of t represents the tangent vector to our space curve. It tells us instantaneous velocity, just like in Calculus 1, f prime tells us instantaneous velocity or instantaneous rate of change. So if you imagine a particle traveling along our curve r of t, that r prime of t represents how fast the particle is traveling at the point P, and it also points in the direction of travel. So our tangent vector points in the direction of travel of our particle along the curve. Which is kind of nice, because if we don't know necessarily the direction of our curve, finding the tangent vector r prime of t will give us that direction. So r prime of t, this is always a vector. All right, so let's think about how we might evaluate the derivative for a vector function. So let's suppose that our vector function r of t in space has 3 components, and in each component we have a function. So I'm going to write this f of t in the x component, g of t in the y component, and h of t in the z component. When we find the derivative of our vector function, we're going to take the limit as delta t approaches 0, and r of t plus delta t would mean that in our I component, we're going to have f of t plus delta t minus f of t I hat, plus in our y component, g of t plus delta t minus g of t j hat. And in our z component, I'm running a little bit out of room, so I'm going to write it underneath. That's going to be h of t plus delta t minus h of t k hat. And all of this is over delta t. we can separate this into three limits. Since we know that evaluating limits of vector functions, we can evaluate them component-wise. And we're going to get that r prime of t will be the limit as delta t approaches 0 in our first component of f of t plus delta t minus f of t over delta t. And this is I hat plus, again, the limit of the second component, limit as delta t approaches 0 of g of t plus delta t minus g of t over delta t. So we're also distributing the delta t, j hat. And for our last component, which I'm going to write underneath, we have the limit as delta t approaches 0, h of t plus delta t minus h of t over delta t, and this is times k hat. Well, what does this give us? This is really nice because you can see that in each component, we're really just evaluating the derivative of a scalar function. So the first component will just be f prime of t, I. Our second component, again, the derivative of g, so g prime of t, j. And our third component, the derivative of h, so h prime of t, k. And that is just looking back at our derivatives in Calculus 1. So this is what we call the derivative, of our vector function, r of t, which means that we can evaluate derivatives component-wise, just like we can do for limits.